applications for highly connected data? All right, we're going to talk about how to design them. It's no easy feat. So a little bit about me. My name is Chris LaCava. I'm the Vice President of product at a company called Expiro. And my background is in user experience design, data visualization, and about 1 million years ago I was a front-end developer, but they don't let me do that anymore. And I'm very passionate about building software that's easy to use, powerful, and elegant. Just a little bit about Expiro. We concentrate on building software for expert users. So a lot of the stuff that you'll see today is geared towards that type of user base, although broadly applicable to a lot of different applications. And a lot of focus is taken at Expiro to basically build these analytics type applications. So everything that you see today are things that is in our wheelhouse. Okay, so what are we going to do today? First, I'm going to give you a couple demos of applications, actual applications running these types of analytics use cases. And then we're going to go through the design patterns and the design systems that we use to decompose these types of problems and build these sustainable, repeatable models. Then I'm going to talk a little bit more about highly connected data just to make sure that we understand really the definition of the thing that we're talking about. And then I'm going to go through some challenges specifically in UX that are particular to this. Maybe not particular, but definitely acute in the area of highly connected data. And then I'm going to talk a little bit about the process that we use to basically explore how we build the design and eventually implement the solution. So, sound good? All right, let's jump in. Okay, so I'm going to give you guys a demo of a couple applications, and I'm going to play the role of the user. So I'll kind of give you what my motivation is here and talk through what we're looking at. So in this first application, this is for people planning a manufacturing pipeline and supply chain. So basically, I'm a planner. Thank you. And I'm trying to figure out how I'm going to get my materials to the right place at the right time, to a factory, for example, in a manufacturing process, to combine them with other components to make bigger components, combine that to make a product, package that product, and then move it over to distribution, eventually sale. So this is, as you can imagine, very, very complex, especially when you're looking at a supply chain across the globe. And we all know that that stuff gets disrupted. It's really hard to forecast and plan and get visibility into some of the problems that we're going to particularly encounter as supply chain planners. So what this system basically does is give me insight into the material flow, the flow of the active ingredients, in this case, in this chemical formulation that we're looking at, all the way through that formulation process, through the packaging and then the distribution. And these little boxes here that I have are, these know facilities like factories. The lines that connect the factories are basically the health of the flow of materials from one step of the manufacturing process to the next. So the color is basically the health indicator. Is it high or low health, meaning of the things flowing through? And the thickness is the volume of material flowing through. So what I basically want to look for are things like bottlenecks, low flow in red, meaning I'm not going to get enough material and it's not going to get to the right place at the right time. So this is a very high level of literally millions of data points across a time series set of data. Tons of information, hard to see in an Excel spreadsheet, but right here, I know that I have information that I'm going to not, and again, this is projected in the future, I'm not going to hit what I need to hit to get these things to market. On the bottom here, you see a histogram that shows me how I can look at this through a point in time, or in this case, a time range. And I can move it back a little bit to see what the underlying causes might have been maybe a month ago, and I can move it forward to see if it's going to get worse and worse. So that is connected by my bill of materials, so each of my independent components here. So I could look at sub-assemblies in this manufacturing process, and it can show me different points in this graph to see where exactly I have an issue. And then I can look at the tabular data that's associated with this and even filter that down. So if I only want to see the acute systems, now I can see really where I have issues. From here, I can run a mitigation strategy. So I know that I have an issue between these two factories. And I happen to know that in this factory, the mechanical resources, the machines that are making the component for the next step, in this case, this packaging material, doesn't have enough capacity. So I'm going to rebalance it. And now I'm looking at the schedule of the machines that run those packaging operations. And what I can see in the red is, as it goes through the time that I've selected, they're either overutilized in red or underutilized in orange. And what I want to try to do is bump them in this middle ground here. I want to make them green, roughly 80% utilized. So it's an optimization problem. And now I can let the system help me. So I'm going to ask it for recommendations to rebalance. It comes back and it gives me a few movements here. And I'm going to say, okay, we'll shift my schedule to try to get more things in the green. It will basically give me that starting point. And then I can take that and see where it changed things to move them around. Again, it's a starting point. I can run more optimization or go in there and change things to make them even more optimized. But then I can compare this with the baseline. So I can basically say, well, what does this scenario look like compared to where I started? And it will give me the deltas, and I can see, yeah, there's an improvement. So this is a case where I looked at a huge amount of information, narrowed it down to a certain time point, narrowed it down to a certain component, then I narrowed it down to a specific location and a specific machine in a location, and then I asked it to optimize, and then I compared. So that is kind of file that away as a set of design patterns that we're going to look at in a minute. Here's another set of design patterns for another application. This, I'm an investigator at a bank, and I'm looking for fraudulent transactions. And I got a tip that someone in our bank, a customer, may be related to some recent fraudulent activity. So I'm going to start by searching for that person. And it comes back and it should tell me, okay, there's a few hits there. I've hit some internal account information, and there's also a company, a party that is associated with that person. I can look at that information and see that, well, let's look at this one and let's check this one. And then I can see its relationships in its network. So how is that person related to different accounts? I can even look at the different properties. So a lot of functionality just within this searching action. That'll come up a little bit later. And I can add this person now to a canvas where I can start to introspect and see the relationships and some of the details around that person, for example, progressively disclose some information around what other parties they're related to and what other bank accounts and addresses they're related to. I can see all that information from here. I could even co-visualize it on a map if I wanted to open up a map and see where it's located here. But what I'm going to do is say, I wonder how this person is related to other known nefarious activity in the bank. And for that, I'm going to utilize some algorithms that are basically going to say, I'm going to go out a set of degrees, 3 hops, 3 degrees out, and say, there's something called the suspicious action report. It's basically in the US, when you find fraudulent activity, you have to report it to the government. I'm going to see if this person is related to any known fraud, any known suspicious activity reports. So I'm going to say, go out 3 hops and just search and find any of these suspicious activities. So it will eventually come back, if the internet's working here, and it will tell me where these things are attached to. And if it well, it timed out, I think, because my internet connection is a little bit slow here. But if it came back, I could say, okay, well, now organize this into groups and let me see how the accounts are related to street addresses, which are allotted to those internal accounts and those addresses. And now I can start to see how my fraud ring is related. And so here I just walk down a path to kind of mental note of searching for a specific data point, seeing the relationships of those data points, traversing those relationships and then organizing them out to see how they relate to other things within a certain taxonomy or categorization. Okay, one more example. Same type of use case, but this time instead of entering from a known search, I'm going to cast a wide net. I'm going to throw out a net to catch a pattern, basically. So in this case, instead of starting with someone's name or someone's account number, I'm going to say all users of my system within a certain risk value, we'll say like a medium risk level, connected to, here, connected to, within 3 hops. And let's say, in this case, this is a reservation cancellation, because that seems to be an indicator of possible fraud. So I'm going to say cancellation. And then I'm going to say within a certain geographical area. So I'm going to get my geographic widget here. And I'm going to say within a geospatial area, and I could select that geospatial area with a map, or I could note it from a list.
I couldn't hear what you said. Sorry.
Okay, so let me select an area, and we will pick on Southern California because it is easy to pick on Southern California. A lot of bad stuff happens there. And there, I've basically built a logical statement now that allows me to cast a wider net. So file that against a design pattern for advanced searching and advanced filtering. Okay, so those are our use cases. So a couple observations on what we saw. You might have noticed some design patterns that don't match a casual kind of customer based mass application. Design systems for these types of operations require specific types of widgets. And we'll go through in detail a few of them. But know that your design system for complex data looks a little bit different. And it oftentimes is tailored to the specific types of users, those expert users. So a supply chain planner may look at material flow differently than a fraud analyst looks at connections between bank accounts. But essentially, when we look at the way that the data is modeled, it's very similar. So there may be tweaks that we employ in these patterns, and we'll go through those patterns just now in a second here. But first, let's talk about navigational schemes. It really matters with complex connected data because you need to know what the user's trying to do. So for example, if you're trying to search in a non-linear exploratory way, basically trying to find what you don't know, because you don't know what you don't know in this case, it's exploratory. You're going to start from a home base, a canvas, for example, to take things on there, and you're going to jump out and do some analysis, drill into information, maybe do a couple of algorithms to analyze things, and then come back to that home base. We call that a hub and spoke approach, and that's a very specific set of widgets and application flows that you use. If they're looking at a known mental model of hierarchy and they're really just drilling down into that hierarchy, that's another view. Now those hierarchies get very complicated, so you have to keep the user in context, but it may be a taxonomy that they know. And that's something that has a slightly different manifestation. That's more of a linear analysis. And then if they're building things like that search set of screens, for example, that is a set of very, very complex actions that they need to do in stepwise process that's often expressed in a wizard. So these 3 examples that we're talking about here, there's many more. These are 3 common ones that show up in this highly connected set of design paradigms. But you could also mix and match these. But you need to know what the user's doing at that point in time to pick the right set of schema. Okay, so let's talk about a few patterns that keep coming up. The first thing that's really important, and you saw me do it a couple times, is searching and filtering. When you get a ton of data and a ton of data that's related, interrelated, you have to know how to search it efficiently, you have to know how to filter it efficiently. So if you think about the gold standard in search, it's probably, at this point, everyone's going to say Google. You type something in there, natural language, and you get usually the results that you want back. Well, unless you have the computing power of Google and you know exactly what people are looking for, a flat list of websites or images or whatever you happen to filter by, you're going to run into a lot of problems. And you saw what I did when I quick search. I searched a parameter, an attribute, but it came back and it said, I found that attribute in all of these things because the thing you're searching on is highly connected. And then you can introspect those things, look at the neighborhoods, look at the properties. The reason why you do that is because when you're running an analytics workflow, taking the result and adding it to your analysis, to your canvas, is usually a big commitment. You may mess up all the other stuff that thing could be connected to. So you have to make sure you basically date your search results before you commit to marriage and you add it to your canvas. And that's a mistake that a lot of designers make, is they try to use basic search paradigms to do something very complex or something very simple on complex data. And here are a few of the anatomical parts of what we just looked at. You've got the categorization, telling people the number of things in each facet or each category, because that really doesn't tell them something meaningful when there's a million things, except that they have to filter more. And then it gives them, some attributes so they can make sure they're looking at the right thing, so they can commence dating their search result. So, then we can jump into more advanced searches, and the one that I showed you, where you can actually build this logical diagram. That's one of many different advanced search paradigms. The thing to note from a design perspective here is this is the 20% rule. Most people should be able to get what they need to get done from a quick search and maybe some filtering, but when they go here, they're invested. And whatever they do here, we ultimately want to save, because they want to do that over and over again and potentially share it. So that's something to keep in mind when you're designing the system. There's a lot of investment in advanced searching, and they're usually computationally very intensive. So they have to be, the technology around them has to be robust enough to be able to have a good user experience. So they are, a lot of times we think of them as totally separate from the quick search. Okay, let's talk about time series, another hot button issue. So a normal time filter, you give me the start date, you give me the end date, and I give you a bunch of data. Well, that would be a huge mistake if your data is highly connected. Because when you look at time series data over a hierarchy, it exponentially increases. You're talking about all those interrelated things, and sometimes the relationship. The information on each of those little points that you want to see is usually has a ton of volume. So you have to tell the user within that series where an interesting point is to look, so they can narrow that down, get context, and then, of course, if they're doing analysis, they're going to want to move it back and see the root causes, and then look downstream, move it forward to see what the future holds for that point in time. That's usually across the board an analysis pattern that most use cases involve. So we basically built a set of these widgets, and we often deploy them. We call it a time slider, and it's basically a little mini application where you saw me use this in the supply chain example, where I was able to see where I should look, where the inflection was of my demand, and then see in that demand spike what the overall view was from the flow of material through those factories. And then I could move things back and forth, and there's stuff to like search for information here, and quick filters to jump to certain points in time that are useful. But where the time slider becomes really useful is when it drives other visualizations. So it's probably pretty hard to see here, but on the bottom you've got the time slider, and it's basically orchestrating all the other data visualizations above it. And that is a very powerful paradigm when people want to see a point in time. So that's another set of patterns that we often employ. Okay, we're going to talk about CoVisualization. Same kind of interface that we were just looking at, but if we break it up into its constituent parts, it's basically a bunch of different visualizations working together. So if you basically change a parameter on one, it can influence the rest of what you're looking at. For example, the time slider sets the aperture of what you want to see in the visualizations, and then you look through different windows, the plot, the list of events, the news, to see different perspectives, different dimensions on usually the same data set. Maybe not always the same data set, but definitely related. And that orchestration of co-visualization between those different visualizations is very powerful to give a user context, a holistic view of a very complex set of data. And then you saw me run the scenario. Co-visualization is also great for comparing two very complex things. So at the click of a control, I could see what changed between my baseline and my scenario and be able to analyze something that's, you know, literally full of millions of data points very easily. And then finally, let's talk about traversing hierarchies a little bit, because if your data is connected, generally you're traversing a hierarchy to some degree. And we often think about network diagrams. In fact, I showed one in one of the demos. They're great for looking at relationships, but they get complex very, very quickly. So that's when co-visualization comes into play. You use filters, you use grids or tables of information to pull out different pieces of that network diagram and show the user what's important. So you can see here the left version is very complex, and the right version, only a segment of a network diagram is popped out. That's because there are other visualizations and other filters driving it. So very important to understand that when you're looking at complex, highly related data, a lot of times you've got to use other primary sources to filter it. And then finally, you saw that flow diagram. It's a great way to show aggregation. So any kind of flow methodology is a great visualization to show highly aggregated connections. And it's a great way to tell the user, hey, there's a problem right here. You're not going to get enough components to this factory at this point in time. Drill in. And then here's a co-visualization where you actually take that flow and you take that network diagram and you show the same type of information. One is the flow, in this case, the flow of funds through, these are basically people laundering money, and then the right side is their relationships. And then of course, pivot grids and data grids are the backbone of this type of analysis. The problem is they can only usually show a couple dimensions. You have to pivot them to see more dimensions. So when you co-visualize it with something like a network diagram where you can show infinite dimensions, it becomes very powerful as both a filtering and categorization technique. Okay, so what are we talking about? Maybe we should have done this first, but highly connected data. What do I really mean when I say that? Shorthand is, well, I'm usually talking about a graph, but they're everywhere basically. You can think about them as any kind of link between a set of entities. That could be a series of roads or railways if we're talking about logistics. It could mean a telecommunications network if we're talking about telecom. It could mean a social network if we're talking about people and their behaviors and how they relate to each other. It could be a bill of materials, the list of components to make a product. We saw that in a couple of the examples that I showed. So when these things are linked together and their relationships matter, well, we can do a lot of analysis around these highly connected data points, these graphs. And there's different ways to store them and model them. We can look at them from a relational standpoint. We get a ton of really cool, very powerful sets of tools there. We could also model them as a graph. We can actually model their relationships as they relate between each other. And that offers us another set of tools. And we can use these things in conjunction. So if we look at a classic data cube, for example, we're talking about slicing and dicing and zooming and sometimes aggregating and pivoting. Super powerful tools. And some of those things we showed in the use cases that I walked through. When we're talking about modeling this as a network diagram, we can think of these things as their relationships really matter, and we can run sorts of analyses on those connections. And you know, some of those analyses, those algorithms that you can run, for example, are dependency algorithms. If you want to find, for example, the point of failure in an electrical grid, sometimes a dependency set of algorithms will work there. If you're looking at finding fraud within a group of accounts in your bank, maybe a grouping analysis or a community detection is going to tell you how those things look. If you want to make like recommendations in an e-commerce system or like Netflix or something, a similarity match might work. If you're looking at trying to get a shipment to the next delivery point in the shortest amount of time, shortest path may work. And if you're looking at highly influential people in your social network, how connected they are in your social network, a centrality set of algorithms may work. So these are not necessarily analogs, but they are good counterparts to more traditional slicing and dicing in a relational model. Okay, so there's a ton of UX complications here. I can probably sum it up in this slide by saying, if we think about a computer processing a lot of information, for example, my laptop, I think about the CPU and the input devices and the output devices and all the buffers and all that stuff. It can run probably millions of data points in milliseconds, maybe billions, I don't know. But I know if we take the human system, our motor system, our cognitive system, our visual system, and you map it to these basically the corresponding pieces of hardware, we are inferior computers when it comes to processing information. Why is that important? So if you're a developer and you're developing a system, don't you want to choose the hardware that has the most weaknesses? That's going to be your single point of failure. Well, it's your user. So if you solve this problem and you figure out how to cognitively get the information to the user without too much cognitive load, all the other technical systems that you have to get to a performance standpoint are a lot easier, because that's going to break first, and usually if you fix that, you fix all the other ones. But there are technical issues. So you're going to get hit on search and filtering if you're searching on highly connected data. You know, you don't necessarily even know where to stop when you search a graph if you're trying to find all the things that are related to that, because you're not getting a discrete list at that point. You're searching collections, and you want to see collections as responses. So that's very difficult, and often, you know, something that takes very specific search techniques, as we saw. Presenting time series information we talked about, it becomes an exponential issue a lot of times when you want to see all those time series points on every single stop in the hierarchy. Pagination can be an issue with hierarchies, because if you cut the pagination arbitrarily in a hierarchy, you're cutting the mental model that the user's trying to keep track of. So pagination is really tricky. We didn't get too much into that in the use cases that I walked through with the demonstrations, but we may look at some things in the future here in pagination. Rendering large visualizations, like trying to render 1 million points in a network diagram, is generally going to crush a web browser. So you want to view that in an alternative way. But I'll tell you that before it crushes your web browser, it's going to crush your user's brain, because they're not even going to be able to look at 50 or 100 things effectively in a network diagram. You got to co-visualize, you got to filter down. And then analysis in real time. This is really more about expectation setting than anything else, because a lot of these algorithms that run across a network are something that you're going to want to batch process a lot of times, or you're going to want to run on small amounts of those networks, and it's setting the user expectation of what's going to happen and how you piece those things out. Okay, so we talked about a lot of complex things. Now let's talk about how to fix them. So starting with the design process, this is just a high-level example of the design process. It looks like most processes, but let's talk about the thing that's a little bit different, specifically steps 2, 3, and 4. That's number 1, understanding the data, number 2, being able to categorize the data, and number 3, building the presentation of the information based on that data. And let me stress that this is a design process. Designers should be doing this as well as developers. And that's where a lot of this stuff falls down, that the designers are designing for a fictitious set of data in the most optimal conditions. And that's usually not the case with any data set. So you have to stick that as early as possible in the design process. You have to basically become a student data scientist as a designer to at least understand some of these pieces. And what do I mean by understand them? Well, you know hopefully if you're a designer, you know the context of your user and what their motivations are. If you know their motivations, you know what features in your data they're going to want to see in what priority, the dominant dimensions. So this could be temporal, this could be time-based data, it could be other factors that help the data basically guide the user to find insight. And the best way to show that is to take a use case. So here's a quick use case. This is for a customer service type, sales type service set of insights, a customer 360 view. And what I basically want to do is, number one, find out how my customers are segmented, categorize them, maybe by age, maybe by income. Then I want to see which ones don't trust my set of products or my brand. That's important. I want to see where my unhappy customers are. I also want to see where my influential customers are, because a happy, influential customer makes other happy, influential customers, makes more customers. And the opposite happens if they're unhappy. And then I want to see when I actually engage them, you know, send out emails or I send out coupons or whatever, which one of those things I did is effective. And then finally, I want to see what works and then give them recommendations for other things. So if you like this, maybe you should buy that. And all of these things could be a set of data points that are dominant dimensions that I want to sort and filter in order to achieve this use case. So this basically sets the groundwork for how I'm going to visualize these things. I'm going to set my data visualization, my navigation to map to this. And then since we're talking about highly connected data, let's talk about some of these graph algorithms. Well, customer segmentation, that's community detection. There's a whole host of algorithms that could work there. Highly influential customers, that's centrality. We could use that algorithm to see who's highly influential. We don't have to go ask every customer who they're influenced by. We can consult the data. Meaningful recommendations, well, that could be a similarity set of algorithms. So if our data is connected and modeled in this way, we have a bunch of algorithms we can run. And this is what that application actually looks like. This is actually an application that we're bringing where we're going to be shipping over the next couple months. So here I've got a network diagram that shows all those connections. I see how influential and what the sentiment is for that particular customer, and I can see that stuff over time, and I can even see how engagement mitigates some issues that customer might have, and I see where some of those issues are in the graph here in this case, all within one view. So I can view this customer's interactions, manipulate a couple filters, and answer most of the questions on my use case. Okay, so in conclusion, I know we covered a lot of stuff, but let me narrow it down to a few basic principles. The problems you're going to have if you have highly connected data are you're going to run the risk of information overload. Break the human factor in your computer hardware that you're targeting towards. You're inevitably going to have performance issues, especially if you don't solve that first problem. And you run the risk of your interface becoming too complex. Why? Because there's an infinite amount of ways you can slice and dice data, run graph algorithms, show them in different visualizations. You're never going to pick the right ones. You have to know the motivation of the users. When you know that, even complicated things become simple because you're giving them the right navigation schema to the things that they want to see at that point in time. And so that comes to our strategies. You got to know your user, and more importantly, potentially, you have to know the data that the user is going to look at. You need to know how to aggregate it and how to filter it effectively, and we looked at a couple of patterns to do that, to highlight the information that they want to see. You want to highlight information because at each step in that process, highly aggregated all the way down to the lowest level of details, you're giving them insights to drill in. And that's what makes the design useful. And that is particular to the domain potentially that you're looking at. So you've got to interview those users, you've got to understand what they're trying to do. And then finally, give them those guideposts so they can progressively disclose. Now, progressive disclosure is a methodology that is intrinsic in this because you're basically allowing the user to open up more and more information rather than overloading them. And that technique goes from that set of aggregations and the time slider that we were looking at and drill downs in certain visualizations to get more information. But the key is that the user is doing the progressive disclosure because they're mapping their exploration to their mental model as they progressively disclose. And the mental model that they're building for exploration is as important a lot of times as the results of that exploration, because how they got that information is the analysis, and it has to be repeatable, and it has to be provable when you're trying to, for example, investigate someone for fraud. Okay, great. Thanks for your attention. Any questions? Awesome, I answered all questions. Yeah.
If I'm a developer, how do I help you do any of this? Because I'm not a designer.
If you're a developer, you're a designer. You might not know it, but you are. No, I'll answer. Yes, it is a cheap answer, yes. Let me elaborate. So data design, especially data design, I could say this for all UX design, but data design is a collaborative effort. A UX designer can't do it alone, but they should be able to be involved because they're going to bring us a piece of the equation that you as a developer may not have insight in, the user context a lot of times. But you may have the set of information that a designer doesn't have, which is if you try to look at these two things or add these two numbers together or divide by 0, this entire application is going to crash. If this entire application crashes, it's the worst application in the history of applications because it's unusable, right? So, so the design process, you know, from this perspective, it is from a designer's perspective, but the point is that it's a collaborative effort, and even a back-end developer is someone who gives a lot of insight into those initial design steps that we looked at in that design process. Any other questions? Okay. Did I talk too fast? Yeah. Oh yes, okay. So the question is, are there other resources to learn about these type of design methodologies? The answer is yes, but they're fragmented, and often they come out of data science discipline. So they haven't made their way into, for example, a lot of curriculum for doing visual design or interaction design. Although that's changing because a lot of this stuff is becoming more and more ubiquitous. I would say for this particular methodology, this is a lot of trial and error, a lot more error than success in a lot of cases, but a lot of it is specific to a set of technologies that there's a lot of focus right now on for designing. It's at least in the graph case of technologies, that is graph databases anyway. That's a relatively new set of technologies that we're just starting to see come into production in a lot of cases in consumer-based applications or wide area of available applications. So the resources that are there from a design perspective usually come from a data analysis standpoint. But that's changing. Every year becomes more and more common in design circles. Okay. Great. Well, thanks everyone. Thanks so much.